limiting reactant and the excess reactant based off of this formula over here. Here we have hydrogen gas added with oxygen gas to give us water. Now, the way that we would actually solve this for the limiting reactant is by first finding the amount of moles that both of the reactants possess, right? Because the limiting reactant only looks at the reactant side. It does not look at the product side. And before we actually get into the calculation, you need to understand what limiting reactant actually means. And it's very simple. When you have a chemical equation, there's going to be a reactant that runs out first, meaning that its whole volume or its whole mass has been consumed during the reaction. And once that happens, everything else is stopped, which means that the excess reactants are just the other reactants, in this case, either the hydrogen or the oxygen, which still has some of its mass remaining because of the fact that the other reactant has been fully completed. It's been fully depleted. So to actually find which one has the limiting reactant, which means that which one runs out faster in our chemical equation, you would use the following steps. You first find the amount of moles. The first thing is you find the moles, right? And the way you do that is by taking both of your reactants. You ignore the stoichiometric coefficient, right? Remember, the stoichiometric coefficient is just a number, the coefficient that's beside your equation, or beside your specific element. So this would also be a stoichiometric coefficient, but obviously this is on the product side. Okay, so you're gonna take this first. So you're gonna first find the amount of moles. So the amount of moles for each reactant. So in this case, that's going to be first finding for H2, right? So how much molar mass would that have? Well, one hydrogen has 1.01 grams per mole. And it's just going to multiply that by 2 to give us 2.02 grams per mole as our molar mass. This comes directly from the periodic table. Then your lowercase m, which is just your regular mass, is going to be 20 grams because that's what the question has specified. And then the moles is what we're trying to find, which has the formula mass over molar mass. So it's just going to be 20.0 grams over 2.02 grams over mole, right? And if you look at this, the 2 grams cancel out. You're just left with mole, which makes sense because N is your mole. So that means that this is going to be 20.0 divided by 20.02, which gives us 9.900910. And obviously that's going to be with moles. Cool. So this is the moles for hydrogen gas, right? Hydrogen is a diatomic molecule like oxygen. That's why it has to have this 2 over here. Right? Okay, next up, we're going to find the moles for oxygen. Again, we're going to first find our molar mass for oxygen, which is just going to be 16 multiplied by 2, right? Because 16 is the molar mass of one singular oxygen. And that gives us 32 grams per mole. And then our lowercase m is just going to be 60 grams because the question has specified 60 grams of oxygen. So that's how much we have. And then our mole count is just going to be, again, the same formula of mass over molar mass, which is 60 grams over 32 grams over mole. The grams cancel out, you're just left with moles. And then the final answer is going to be 1.875 moles. Okay, The first step is done. You found the amount of moles. But what are you even supposed to do with this? This doesn't mean anything yet. Well, here's what you're going to do. You found the amount of moles for two hydrogens and two oxygens. However, to actually compare the real amount, because what these moles essentially tell us is they tell us how much content of hydrogen and of oxygen we have. So based off of that, we can compare which one is the lower amount, right? Because logically, think about it this way. A limiting reactant, the understanding needs to be solid. A limiting reactant is one of the reactants that runs out first. If it runs out first in a chemical reaction, that means it has to have the lowest amount of content within it. Because how else is it going to run out first? So, by finding the moles, we take these and we compare them. However, you can't compare these two mole counts because these two mole counts uh, have two oxygens within them and two hydrogens within them. So now you're going to take your stoichiometric coefficient and you're going to divide it. Okay? So you're going to take your stoichiometric coefficient, which is in this case 2 and 1, and you're going to divide by that. So then you just find a more normalized amount that you find per each stoichiometric coefficient, which is exactly what we want. So we're going to divide by stoichiometric. First for hydrogen, which I use this color for. So hydrogen had a mole of 9.9010. We're going to divide that by 2 because the stoichiometric coefficient is 2. Divide that by 2. What does that give me? It gives me about 5, so 4.9505. Okay. Now we're going to do the same thing for oxygen. However, for oxygen, our work is already cut out for us because the stoichiometric coefficient is just 1 over here. It's 1 over here, right? So for oxygen, it's just going to be 1.875 moles over 1, which gives us the same thing, 1.875 moles. Now you compare these two mole counts. Which one is lower? It's the oxygen. So that means that oxygen is our limiting reactant. So I'm going to say here, O2 is which is oxygen gas, is our limiting reactant. And I'm going to just delete this over here. Reactant is just going to be the other reactants. It doesn't necessarily need to just be one, there could be multiple other, but all of those are going to be the excess reactants, right? Because some part of whatever was given, so in this case it was 20 grams, right? Some part of that 20 grams is still going to be remaining. Okay. So yeah, that's the reasoning behind this. And now you might be a little bit confused as to like why exactly a lower amount of grams would be the excess. The reason for that is because hydrogen, its its mole count, its mole count is more. Okay? So we're looking at this in the sense of the moles. The moles have to be the smaller one, right? So you have to look at the smaller mole count, and that would be the limiting reactant. So the excess reactant, which is left, is going to be nitrogen. So H2 is our excess re So that's how you're able to identify the actual the actual limiting reactant and then the excess reactant. And also the definition of the mass of the water, well, then you're just gonna have to use the moles, and specifically mole to mole ratio. Right? So you take whatever mole you have for uh for the limiting reactant. Right? You have to always use the limiting reactant when finding these questions out. So that would be oxygen, right? So that has a 1 stoichiometric coefficient, and then the water has a 2. So to figure out, so this is question A and B, right? Now to figure out question C, here's what we're gonna do. So, what you're gonna do is, first of all, figure out the amount of moles, the amount of moles for water. You already know the amount of moles for the other part of the ratio, which is oxygen, so just find it out for water. And that is going to be this. Remember, we don't count the stoichiometric coefficient here, so this 18 grams per mole is just this part over. Actually, to be a little bit more accurate, just because we were being accurate from before, it would actually be 18.01. It doesn't really matter. The mass is going to be what we're trying to find, and then the moles is what we're trying to find. Oops. Well, my glitching out. Cool. Okay, so the moles is also what we're trying to find. Let's first find the amount of moles. The way we're going to do that is through the mole ratio. The mole ratio states that for every 1 mole of oxygen gas, there's going to be 2 moles of H2O. So we could just do cross multiplication. We know the amount of moles for oxygen, which is 1.875. 1.875. So you're going to just take that 1.875 moles, and that's over 1, which is your stoichiometric coefficient. And that's going to equal 2 over 2 because it's 2 moles for the water. These are stoichiometric coefficients, but they also represent the mole to mole ratio, which is just telling us for, this amount of moles in oxygen, there's this amount of moles for hydrogen. And moles is like the standardized like way of counting elements, right? That's how I like to think about it. It's like the standardized way of counting elements. But okay, if you do cross multiplication, it's just n equals 2 times 1.875 moles, and that gives you 2 times 1.875. That gives you 3.750 moles. So the amount of moles that you have of for water is going to be 3.750 moles. And I think it'd be more appropriate to move this part over here. The mass. For the mass, it's just going to be the amount of moles multiplied by the amount of mass, molar mass. So then that's just going to be 3.750 moles multiplied by 18.01 grams per mole. And that gives us 3.75 multiplied by 18.0. 67.5375 moles. You want to use significant digits. So in this case, our significant digit would have been 3, right? So kind of like physics. You have 3 significant digits here. That means we're going to take three significant digits from here, which is 67.5, 67.5 moles. So that's how you solve everything over here. I'm going to skip the mass of the reactant remaining because it's pretty straightforward. But yeah, that's how you find the limiting reactants by first looking for the amount of moles and then dividing that by your stoichiometric coefficient, taking on the lower count because the lower count will run out faster because it's a lower amount, which is exactly what the limiting reactant means, right? And then whatever is remaining, the other reactants are your access reactants because they don't run out once the limiting reactant runs. So there's going to be some excess amount associated to them after the chemical equation finishes or the chemical reaction finishes. Hope this helped.